Hey everybody, it's Code Webda here. Sorry I've been away for a bit. I kinda was dealing with the coronavirus pandemic, but I'm back. So today's video is going to be focusing on using TensorFlow, right? I don't know if you watched my other videos, you can see how TensorFlow actually works. We're going to use this online program called Google Colab, and essentially that helps us streamline our process. So in TensorFlow, which is a machine learning library, um, we're going to actually be able to detect cats or dogs. I'm going to show you two methods in which we're going to be able to do that. So first of all, we're going to start with using a vanilla neural network. If you haven't heard of it, don't worry. It'll make sense as I go through. But yeah, let's get right into it. So what you want to first do is search up Google Colab, and that should load you up. You're here. And it's going to say welcome to Collaboratory. It probably should load faster for you. And essentially you'll sign in with a Gmail account, whatever your Gmail account is. I'm not going to sign in. And then I've already signed in here. You're going to, actually let me sign into my other account. Actually, don't worry. You're going to create a new notebook, file new notebook. And the reason I'm using Google Colab is so we don't have to go through that horrible process of downloading TensorFlow. It takes hours and it's just a pain in the ass. In Google Colab, it basically does all your installations for you, and you can just import TensorFlow. Okay, so before we start, we want our Google Colab to use a GPU. I've bought the premium. You can buy it as well. It's only like $5, not expensive. But essentially, you will only have this one, and you're going to press GPU. If you bought the extended one, you've got high RAM, and you get like a TPU. But if you've only bought this, you get like CPU and GPU. So all you're going to do is save there, and that should say all changes saved. Connect it, and that should connect. So first of all, what we're going to be doing is we need to import several packages. Um, so let's go ahead and do that. So what do these packages actually do? NumPy is basically for data manipulation. TensorFlow datasets is actually importing our cat dog dataset, and we'll use layers here in Keras to actually do image manipulation. So now what we're going to do is actually just import it using TFDS. Okay, so now we've got our actual data set. Just to show you what type this is, I'm going to go ahead and print total set, and you'll see it's not an actual array, it's a special TensorFlow data type. And so I'm going to show you how you can actually extract that data into corresponding normal data. And so this should just load. It's downloading preparing all the data sets and downloading it. It shouldn't take too long. Okay, guys, we're back. Essentially, you can see here, it's got this option data set. It's just a weird set. So I'm just going to show you how you can actually extract that data into a corresponding Python array, and we can use this. So in our case, we want our images to be 64 pixels by 64 pixels. So before we go ahead and extract the data, we need to create a little function using Keras to resize our images to this size. We also want to do some special data manipulation because in essentially neural networks, if we have a data set with huge numbers, it's kind of bad for our actual code. So if we had something like this, um, colors only go up to 255. We essentially want to normalize this into like perhaps something like 0.233 to 0.233, and you get what I mean. So what we're going to do there as well is we're going to divide all our values by 255, and that would essentially force us to be in between 0 and 1. And that just makes our network function better. Otherwise, it's just like jumping all around and it's not real good. So let's go ahead and actually do that. And so yeah, that's our actual resize functions. We've got image size. We're going to use 64 pixels here just for processing speed. We got resize, rescale, and this will be used in our code later. And as you can see, it resizes to 64, and it uses an offset -1. This essentially just goes 1 divided by 255. I think this works better. And so this will just rescale our images, normalize our code. So next what we want to do is we want to separate our data set into image data, right? So the actual image and its corresponding labels. The labels we're going to be using is really simple. So 0 is for cat and 1 is for dog. So we'll also transform obviously our arrays into something called numpy arrays. Numpy arrays are really good because you can do a lot of things, like it tells you shapes, it tells you a lot more information, and numpy is a really good open source package that's been built for like for a couple of years. So let's go ahead and actually do that. Okay, so let me just explain what's happening. So let me quickly change that to capital Y. So you've got the train X. X obviously is for images. Y is for the labels, and that's just a neural network convention. So we're going to loop through it. So that's how we actually get the data from total set, because it's an interesting data type. We're going to loop through it. Just keep this as a tally. Sometimes what happens is the RAM overflows. So what you can do is you can basically say if I is some number, cut it there. Shouldn't matter this time. But what we're going to do here is we're going to append an array, right? So NP array. We should start here. We got the actual image from our data. So you got example image. We resize that image, and then we just change that into a numpy array. We get our label, and that's basically labeling. So it's going to be train Y, and we change that to an array. And one more thing I should do is I'm just going to show you what this actually looks like. This sets it as NP array, and this is basically all our pre-processing done. Well, so far. So let's go ahead and run that. Okay, so we've got a little bit of an error. All right, guys, I'm back. So what I essentially, all I did was I just forgot to put a comma there. There wasn't a comma here, which is pretty stupid of me because this is a list and you need a comma. So yeah, I just ran it afterwards, and it ran about 23,000 times, which makes sense. So you've got 23,000 inputs here, 64, 64, 3, which makes sense. But our label has an error, so I'm going to go fix that error pretty quickly and come right back. So yeah, guys, I don't know what happened there. I kind of just deleted this line somewhere along the line. But yeah, you're just supposed to have this. I think that's the right indentation now. Get rid of one bracket. But yeah, you're just supposed to have this. So just make sure you have that. I must have just accidentally deleted it without noticing. And I'm going to run this again and come right back. Alright guys, so now that we've got everything running, you should see that the first data set has 23,262, or if it for some reason stopped before that because it can't run that much RAM, it should show another number, but needless to say, it's in between 20K and 23K, which is the max number. So we've got 23, we've got 64 by 64 by 3. So 64 by 64 is obviously the pixels, and then 3 is just the corresponding color to each pixels, and then we've got 23,000 labels, 23,262. So what we next want to do to make our code run a bit smoother, actually I'll show you how to do it both ways, but what we're going to do first, the first way, is we want to change our images to actually be from color to gray. So that will help our neural network run faster. So let's go ahead and actually do that. Okay, so we're back. So what we essentially did is we created a new array called new train X. And so for each image in train X, we basically want to just do that function onto the train X image. So change it from RGB to gray. and we want to change that neutron x to an array, and we also want to reshape it because in neural networks how it actually works is that it takes, for instance, if you've got 20k inputs, so what it does is it separates those inputs, and each time it runs through the neural network it runs it just with the other two. So we want it just to use 64 times 64 images. So this is just how neural networks work, right? So I've made a video about neural networks, which I'm gonna link. I've linked in the description. You can check my channel. It explains it a bit more in detail. But essentially, you just need to multiply all the instances, so you only get one input instead of a double array coming into the neural network. So I want to show you the actual shape, showing that it actually works. Hopefully, we don't get any errors. Invalid syntax. Hey guys, so we basically just had a bracket there. So let's try it again. It might take some time, so I'll come right back. Oh, no, it's pretty fast actually. So yeah, we've got 23,262 and 64 times 60. So let's go ahead and finally actually get to the bread and butter of our system. And we're going to actually build our neural network. So this is developing the model. Okay, so now that we've actually built up our model and got it compiled, we want to actually run our model. And so what we're going to be doing is we're going to have two sets of data. We're going to have 1,000 pieces of validation data. And so the reason we use that is because something called overfitting, right? So our neural network basically can memorize our relations, and that's called overfitting for our training data. So what we do is we separate the training data and some extra data, and so the extra data will be like a control. So we'll look at the data and be like, hey, actually your training data shows that it's like 100% accuracy, but in real life, it's only about 50% accuracy. All right, so make sure you always do that separation. Okay, so yeah, we've separated it into two batches of 1,000 and whatever your other numbers minus 1,000. And we're going to use this history function or the history variable to store whatever we fit through here. It's going to run for 100 epochs. It's pretty nice. We're going to use batch sizes of 128. So each time it's running through, it's going to use 128. And we're going to do the validation data, obviously, val x, val y. So if you should go ahead and run it, probably get some errors as I usually do. Name sigmoid is not defined, so let me go fix that. Okay guys, so I think it's just that. Okay, so it should run through. It will take some time because you're obviously going to be running 100 epochs. It's faster on mine with higher RAM, and I'll be right back. Okay, we're back guys. So as you can see, we've got our loss here, our accuracy, that's the training accuracy. So as you can see, it's got like a 98% accuracy for our training data, which is obviously because of overfitting. And then we only have like a 62% in real life, right? So that's the real life. But let's try to display this in a bit more beautiful fashion. And that's what we're going to use matplotlib for. So let's go ahead and try to do that. Okay, so what we've essentially done here is, as you can see, the history stores some really important values. So if you go history.history val accuracy, it'll give you like a list of all the value accuracies, so the real accuracies, and then accuracy will give you the list of training accuracies. Epochs here is just going to be the length of, so we're just going to call like 0, 1, 2, 3, 4, 5, 6, 7, up to 100. We're actually going to plot our values here. And yeah, so you should see this, hopefully if we don't get any errors. And yeah, so why does that look bad? Sorry guys, let's just change that to blue so it looks a bit more appealing. Yeah, that's a bit better. So what the red is the training accuracy. As you can see, past, I don't know, about 5 epochs, it just skyrockets to 1, right? So it's getting memorizing some inbuilt functions. I don't know what the hell it's doing, but essentially this is called overfitting, right? In real, if you train it on real data like we did here, you're getting an average of about like 60 to 65%, max value being at 65%. So I'd say a median value would be about 64, 63, looking at the peaks and everything. So we got 63% accuracy rate here, which is not bad on a vanilla neural network, but it's it's pretty crappy when you're using it in real life, right? So what we're going to do next, really quickly, is we're going to copy all our data again, and all we're going to do is train our system on colored images instead of grayed images. So go ahead and create a new code. And go up, and we're just going to copy everything here. Just going to copy everything there. Put it there, and all we're going to do here is we're going to change this to ×3, okay? And that just means we have to incorporate the colored portion. So where is our new train x? So for train x, we're actually going to reshape train x. So we're going to go train x equals train x. I don't know if I should have to actually say equals. Yeah, I should. I kind of forgot. So let's go ahead and just let's just copy that. Sorry guys, so I just forgot to tell you, you just have to get train X and change new train X that was here a second ago. So if I change that to train X here, because we're going to be using that instead. And let's go ahead and run it. All right guys, so that finished running. So let's just make a new code block, copy that, and just rerun this. And actually, yeah, we get a slightly higher accuracy rate. So the colors actually do help. I don't know why. Maybe dogs are a bit more brownish or something along the lines like that. But as you can see, it does help a bit. And so yeah. So anyway, guys, next time what we're going to be doing is we're going to rewrite this, but with a convolutional neural network, which is a different type of system. But yeah, thanks for watching. Hit that subscribe and like button, and CodeWeb, they're out.